Hi everyone, my name is Santiago and I'm gonna present our work in switching algorithm for safety under denial of service attacks. Um, Consider to motivate our problem an example in which we have attacks in the sensor data of a system and the attackers are capable of disabling the transmission of signals between devices, and this is what we know as denial of service or DoS attacks. This will lead to potential violation of safety requirements. So the goal of our work is to keep a system's trajectory in a safe set, even under denial of service attacks. And we do it by designing a control algorithm that will bound the impact of the system based on the available information to guarantee safety. We will assume that the attacks have finite duration and that they're succeeded by intervals of no attacks. So just to provide general definitions, consider the nonlinear system given in terms of a differential equation with a flow map F and an output equation with an output map H. We define conditional invariance of a set with respect to S with respect to a set M if every trajectory that starts in M remains in S at all times. And we use this property to encode safety of a system with respect to a set x0 and a set xu, such that every trajectory that starts in x0 will remain outside of xu at all times. So the dynamics that we're gonna use during this work are linear. And the output function is given in terms of a matrix C that has two components, the tilde and C bar. So we have an attack such that the measured output after an attack has two components. Outputs that can be secure, YS, and outputs that are vulnerable for being attacked, YA. We can say that YA will take a value of C bar X if there are no attacks, but when there are attacks and there are denial of service, they will take a different value, for example, a null value. And we denote by calligraph TA the set of times of attack that we assume as known. We know when attacks occur and when they end. So consider an example in which you have three outputs. Two of them are secure in the top of the figure, but there is one that is vulnerable to attacks. So after an interval of no attacks, we have an attack that has maximum duration of TA seconds. And after each of attacks, we have intervals of no attacks of at least TNA seconds. So our goal is to find a set of initial states and design a control law based on the available information such that if we initialize correctly our trajectories, they will remain in the set S at all times. And we do this based on a control design relying on an observer. So the intuition how it works is under attacks, we use the non-attacked outputs. But when we are not under attacks, we can use the complete output vector. This is the structure of our observer, where x hat is the estimator, and we want to design the functions g1 and g2, and this is the structure of our controller. We want to design the functions kappa 1 and kappa 2 that rely on the available information. We want to design the sets of initial states of estimates before and after an attack. So if we properly initialize the state and estimation, we can guarantee that the trajectories will remain on S during attacks. The same thing we can guarantee when there are no attacks, but we will get ready for the next attack by ensuring that at the end of an interval with no attacks, we'll respect some bounds on the error. So this is the general scheme of our approach under nominal operation. Then we have our control and observer working, but whenever an attack detector spots that the vulnerable outputs have been attacked, then it triggers a switch. So we use our recovery control and recovery observers. And whenever the attack detector recognizes that the attack has ended, we can back to nominal operation. Well, we assume that the system is controllable and detectable, and the idea is that when there are no attacks, all the eigenvalues of the observer will be on the open left plane. But under attacks, there is a potential drop in the rank of observability. So some of the modes can be non-observable, but we can design our observer such that the greatest amount of eigenvalues of the observer will be in the open left half plane. And we do this by denoting the dynamics of our error E based on the observer and the state dynamics. So our first result basically says that under intervals of no attacks, if the initial error is bounded by E bar 0, then given that our system is observable, we'll expect the error to exponentially decrease. So we can bound its norm by a function gamma 1 that is exponentially decaying. Under the case of attacks, we will have a bound gamma 2 on the error if the initial error is bounded again by E bar 0. But in this case, we will expect the error to have some components that lead to a decreasement based on the observable modes, but based on the unobservable modes, it might increase. So our bound is the worst case value during that interval that is finite. If we use this information to analyze the error under every sequence of attack, non-attack, attack, non-attack intervals, then we can guarantee a global bound, and we can also guarantee that the error will be smaller than the initial error at the end of every interval without non-attack to prepare for the next attack. So if we have this, we have a global bound in the error, and this is what we're gonna use to design our controller. So we have already the structure of our switching observer, and we're ready to design the controller. But before, we need to define some sets of interest. So assume that you define a set S, that is the set you want to render safe, and the set of initial states x0 is a definition of epsilon by epsilon of the set S. If you select an initial condition and the initial error is bounded, then that means that the initial estimation has to be inside of an E-bar ball of the initial state, and this gives us the set x tilde, that is the allowed initial estimates. The next result we have says that if we have a bounded estimation error and a proper initialization of the trajectories, if we render the estimation to state inside of the red set of the red set, this will imply that the state will remain inside of the safe set because the error is bounded at all times. So the objective of our control will be to enforce the estimate to remain inside of the red set at all times to guarantee safety of it. So we use a zero sub-level set representation of a subset of the red set that we'll call x bar in terms of function h, a CBF function, and we want to design the feedback loop based on the estimation to guarantee conditional invariance. So we do it based on these two control barrier functions conditions, respectively, when under no attacks and under attacks, and we encode them based on these quadratic programming problems. The solution of these two equations, respectively, under no intervals with no attacks and intervals with attacks, will give us the controller that will render the estimation to remain instead of the red set. So if the QPs are feasible in the steady space of the estimation, and we properly initialize based on the construction of our sets, both the state and the estimation, then we can guarantee that the estimation will remain inside of the set that we define based on our function h, that is x bar, and this will imply that the state will remain inside of the safe set. This is thanks to the feasibility of the QPs. So now we have our complete scheme, and we are ready to present an example in which we have a system as a modified double integrator in which the state is x1 and x2, but we include this term in the dynamics of x1, and the output y allows us to measure both of the states, but the state x1 is only available when there are no attacks. So the goal, again, is to render the yellow set as forward invariant, or all the trajectories to remain inside of S at all times. So we select a text of maximum duration of 1.6 seconds, and you can see how small is the time window that we need after each of the tags to guarantee that will remain inside of it. But what if we don't respect this design? What if we just have attacks that are longer than this design? Then we can see in the top plot that if in purple we're displaying the estimation of our first state, yes, we guarantee that it converges to 0. But the actual state is really far from that estimation. So the error will diverge as its norm. And even though we have trajectories for our estimation that remain inside of our that was constructed based on the barrier function, the actual state is actually diverging and violating safety requirements. So if we construct properly our sets and the attacks are inside of that window that we define, then we can see how the estimation converges to the actual state, right? So during attacks, we see how the error increases, but it will decrease under those intervals of no attacks in which we have complete observability. So based on the bounds analysis of the estimation error, we can see how there is a global bound presented in purple. So the error is always respecting that bound, and it will be ready for the next attack interval by remaining under the initial error. And this is the basic intuition of our algorithm. So if we have that condition being respected, the error will be bounded at all times, and based on our QP's solutions, we have a control action that will render the trajectories inside of the state inside of S at all times. Okay, as a conclusion, we presented a switched controller with a switched observer to recover safely from DoS attacks in the sensors, and we encode conditional invariants by employing a barrier function approach while bounding the estimation error at all times. Future work includes employing a finite time observer and a tighter bound that will relax a little bit the conservatism that we have in this work. Thank you for your attention, and I'm happy to receive any questions via email.